This is chapter 21, part 7. We're going to look a little bit more in detail at blood pressure. So in the past couple of videos, we've kind of gone over quite a few of these factors that are going to affect blood pressure. So on the left here, we have these changes in green boxes that are all going to increase cardiac output. On the right, we're going to have these blue boxes that are going to be changes that increase systemic vascular resistance. And then increases in cardiac output and increases in systemic vascular resistance are both going to influence an increase in the mean arterial pressure. So at the top here on the green boxes, we have that increase in blood volume, the skeletal muscle pump and the respiratory pump, as well as venoconstriction are all going to influence that increase on venous return. Now the increase in venous return together with the increase in sympathetic impulses and hormones from the adrenal are both going to contribute to increases in stroke volume. Now these sympathetic impulses along with decreased parasympathetic impulses are going to contribute to an increase in heart rate, and then that heart rate and stroke volume both increased are going to increase cardiac output. Now on the other side here, in the blue boxes, we're going to have that increase in red blood cells is going to cause an increase in blood viscosity. Remember, we're going to have more red blood cells with respect to the fluid is going to cause the fluid to flow less, have a higher viscosity. This is going to be kind of the difference that we see between something like water with a very low viscosity to something like syrup or ketchup or something like that. Something that's thicker as a fluid is going to have a higher viscosity than something that is thinner. Then increase in body size is going to increase that total blood vessel length. And then along with the increased blood viscosity, increase in blood vessel length, and a decrease in the blood vessel radius, like in vasoconstriction, are all going to contribute to that increase in systemic vascular resistance. Now we don't need all three of these to increase the resistance. These are just three that contribute, and even one of these occurring is going to increase the vascular resistance. If all three are occurring at the same time, then that vascular resistance is going to be increased by quite a bit. So we've seen this diagram before, looking at the input to the cardiovascular center and then the output to effectors. So several of these interconnected feedback systems work to control blood pressure by adjusting the heart rate, the stroke volume, the systemic vascular resistance, and blood volume. So remember, the cardiovascular center here in the medulla oblongata helps to regulate heart rate, stroke volume, and also blood volume. Now the cardiovascular center receives input, remember, from these higher brain centers and also from the sensory receptors. So it's going to get all that input here coming in. And then output from the cardiovascular center is going to flow along these sympathetic and parasympathetic neurons in the autonomic nervous center. And the sympathetic impulses are going to reach the heart by the cardiac accelerator nerves. And this is going to work to increase the heart rate and contractility. And it's also going to reach blood vessels by these vasomotor nerves to cause vasoconstriction. Now parasympathetic stimulation is going to be conveyed along the vagus nerves, and this works to decrease heart rate. Now baroreceptors, these are pressure sensitive sensory receptors. These are located in the aorta, right here, so here in the aorta, and also in the internal carotid arteries. So these are here, these internal carotid arteries. These are arteries in the neck that are going to supply blood to the brain. We do also have a couple of baroreceptors in other large arteries in the neck and chest, but these receptors are going to send impulses to the cardiovascular center to help regulate blood pressure. So the cardiovascular center is indicated right here. Now these baroreceptors actually get us what is called baroreceptor reflexes. Now the two most important baroreceptor reflexes are going to be the carotid sinus reflex and the aortic reflex. So baroreceptors in the wall of the carotid sinuses, these are the actual nerves or sensory receptors that are going to initiate the carotid sinus reflex. And this is working to help regulate blood pressure in the brain. So this helps to regulate in the brain. And then baroreceptors in the wall of the ascending aorta and in the arch of the aorta are going to initiate this aortic reflex, and this works to regulate systemic blood pressure. So here we have negative feedback regulation of blood pressure. This is by the baroreceptor reflexes. So here we have decreasing blood pressure. This is when the baroreceptors are going to sense that decreasing blood pressure. So in the carotid sinus and the arch of the aorta. And they're going to send signals to the cardiovascular center in the medulla oblongata and also to the adrenal medulla. And they're going to send impulses to increase the blood pressure by increasing the heart rate and the constriction of blood vessels. So here we have that output from the cardiovascular center to be that increased sympathetic stimulation and decreased parasympathetic stimulation. And the output from the adrenal medulla is going to be increased secretion of epinephrine and norepinephrine. So then this output to the effectors is going to increase stroke volume and heart rate, all that leading to an increase in cardiac output. And then on the other side here, we're going to lead to that constriction of blood vessels, increasing vascular resistance. So those together, well, really separate as well, but together they're going to really work to increase that blood pressure and return us back to homeostasis. Now, this table here shows the blood pressure regulation by hormones. It pretty much shows what hormones do what. So it has the hormone list here and their effect on blood pressure. Now, several hormones are going to regulate blood pressure and blood flow by changing the cardiac output, by changing the systemic vascular resistance, or by adjusting the total blood volume. So there's a couple different things that are going to do this. The first one is the renin-angiotensin-aldosterone system. So remember, this is the pathway that actually raises blood pressure by increasing systemic vascular resistance. And as well, it stimulates the secretion of aldosterone. So we're going to stimulate the secretion of aldosterone, which increases blood pressure by increasing that water absorption in the kidneys. Next is going to be epinephrine and norepinephrine. Now, in response to sympathetic stimulation, the adrenal medulla is going to release these hormones that are going to increase cardiac output by increasing the rate and the force of heart contractions. Next, we have the antidiuretic hormone. This is also just called ADH. And this is, remember, produced by the hypothalamus, released by the posterior pituitary. And this causes vasoconstriction. So here, this would be antidiuretic hormone here. Cause vasoconstriction, which is going to increase that blood pressure. Lastly is the atrial natriuretic peptide. Or ANP. And ANP is actually going to lower blood pressure by causing vasodilation and also by promoting the loss of salts and water in urine, which is going to decrease blood volume. Now, the ability of tissue to automatically adjust blood flow to match its metabolic demands, this is called autoregulation. So in tissues like the heart and skeletal muscle, where demand for oxygen and nutrients, as well as demand for the removal of wastes, can increase extremely during physical activity, as much as even tenfold, autoregulation is really important to increase blood flow through that tissue. Now, there are two general types of stimuli that cause autoregulatory changes in blood flow. The first one is physical changes. So physical warming is going to promote vasodilation, and cooling causes vasoconstriction. So an example of this is when you exercise, your muscles are going to get quite warm, and as a result, the warmth is going to cause vasodilation, which increases blood flow to those tissues. Here we have the second stimuli that causes autoregulatory changes, and these are vasodilating or vasoconstricting chemicals. So there's actually several types of cells that can release a variety of chemicals that alter blood vessel diameter. So these are going to be your two types of stimuli that can cause autoregulation. And that's going to be the end of Chapter 21, Part 7.